A relation shows how one set of numbers is related to another. The set of input values is called the domain, and the set of output values is called the range. Before we get into a bit about relations, we need to review a few things about the coordinate plane. First of all, we need to know what the x-axis is. So the x-axis is going to be this line here that goes left to right. It is horizontal like the horizon, so the x-axis goes left to right. At the very center of the x-axis is 0, and from here you count outwards to the right and you have positive numbers. So it's good to be right. Being right is a positive thing, so on the right we have the positive numbers. Being left behind is negative. On the left we have negative numbers. Next, the y-axis. The y-axis is this vertical line that we have here. Being up or being in a positive mood is being up is a positive thing. So this is positive. The up of the upper part of the y-axis is the positive part. Being down is considered negative. So the lower part of our y-axis is negative. You'll notice at the center we have 0, and we're counting up to get the positive numbers and counting down to get the negative numbers. The origin is where we start counting from. So notice both for the x and the y-axis we start counting here. So this location here is called the origin. It is not called the center, it is not called the middle, it is called the origin. Now let's look at what exactly are quadrants. If we look at the word quadrant, it starts out with quad. Quad means 4. Just like how a quadrilateral has 4 sides. If you notice that we have actually, by drawing the x and y axis, separated the whole coordinate plane into 1, 2, 3, 4 corners. These 4 corners are called quadrants. And the way that we know how to start numbering them is that we could draw a C. Notice that when we drew the C, we started here, then we went here, then we went here, and then here. So 1, 2, 3, 4. So that is how we're going to number our quadrants. We use Roman numerals for the quadrants. So this is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. In quadrant 1, all of the values are positive. Both the x is positive and the y is positive. In quadrant 2, the x is negative and the y is positive. In quadrant 3, the x is negative and the y is also negative. And finally, in quadrant 4, the x is positive and the y is negative. So if we were to look at the points here that we're going to graph and see whether they fit into a quadrant or not, this one does not fit into a quadrant. In fact, it would be here. So 0, 0 are the coordinates of the origin. So x is 0 and y is 0 at exactly that point. This point 0, 2, we know x is 0, so x is 0 here, y is 2, which means we have to go up 2, so that's where our point would be for our 0, 2. Notice that 0, 2 and 0, 0 are not inside of any of the quadrants. So this point and this point are in none of the quadrants. It's actually on the border of a few quadrants. So for it to be in the quadrant, it has to actually be in here, here, or here, not on any of the lines or not on any of the axes. So what about this point 0, 5? 0, 5, x is 0 and y is 5, so we start at the origin. X is 0, so we're not moving left or right. Y is 5, so we're going to move up 5 and end up at that point. For 3, 0, this time x is 3, so x is 3 right here, and y is 0, so that means we're not going up or down. So 3, 0 would be right here. For 7, 0, x is 7 and y is 0. So 7, 0, we'll find 7 for the x, and the y is 0, so we're not moving up or down. This is where our point would end up going. And just to remind you, none of these points are in any of the quadrants. They're actually on one of the axes. So now we can start graphing these other points, 2, 3. Notice that both the x and the y are positive. And this happens within the first quadrant, so we know our point has to end up here. Please remember the correct order. The first number is x and the second one is y. Sometimes students mix this up. So x is 2, so x is 2 right here, and y is 3, so y is 3 here. So that's where our point would go. For the next coordinate, negative 2, 3, x is negative 2 and y is 3. So negative positive would be in our second quadrant. So x is negative 2. Negative 2 is here for the x. And y is 3. That means we'd have to go up and we'd end up there. Our next coordinate is negative 2, negative 3. So both values are negative. So that would happen only in the third quadrant. So x is negative 2 is here, and we need to go down to where y is negative 3 and end up here. So that's where our coordinate would go. For the last one, positive 2, negative 3, that would have to go in our fourth quadrant. So x is a positive 2, and we go down to negative 3, that's where our point should end up. So that's just a quick review on how to graph, and also parts of the coordinate plane. To answer these two questions, remember that the domain is a set of input values, and the range is a set of output values. Normally the domain would be the x's. Later on you're going to have the domain slightly differently, but in this case the domain we're inputting 2, 3, negative 1, and 0, and we're getting back the y values 4, 5, 4, and 6. So this is how we would write our domain. It would contain 2, 3, negative 1, and 0. So that would be our domain of this relation. What about the range? The range would be the set of other values. So this is what the range for this particular set would look like. So notice that in the range we have 4 and 4. So we don't have to write it twice, let's just write it once. So in the range we have 4. We also have 5. So we have 5. And then we have 6. So those are our domain and range for this relation. If we were to try and figure out the domain and range from a graph, then we're still trying to find out what set of x values and what set of y values make sense. So notice that the x value that corresponds to this point this part of our relation is negative 3. So negative 3 is in the domain. For this point, negative 1 is its x value. So negative 1 would be in the domain as well. This point also has negative 1 as its x value. So notice that if we were to go straight down, we end up at negative 1. So negative 1 is the x value of this point and this point. So again, negative 1 is in the domain. For this point, 2 is its x value. So 2 is also in the domain. This point has 4 in its x as its x value. So 4, also positive 4, is in the domain. 5 corresponds to the x value for this point, and so 5 would be in the domain as well. So this is what our domain would look like if it were written out. So again, just to make sure we understand this point has negative 3 as a part of its domain. This point has negative 1 as a part of its domain. Similarly, if were we to continue, we could see clearly that 2, 4, and 5 are also values, x values, that have some relation to the points that are expressed. We could use the same idea to figure out the range. Notice that this point has 5 as its y value, so 5 is in the range. This point has 1 as its y value, so 1 is also in the range. Negative 1, this point here has 0 as its y value. So does this point. So 0 is in the range. This point has 2 as its y value. So 2 is also in the range. And this point has negative 2 as its y value. So if we were to express it, here's what it would look like. And just to reiterate, this point has 5 as its y value. This point has 1 as its y value. This point has 2 as its y value. This point and this point both have 0 as its y value. And this point has negative 2 as its y value. So you notice very clearly that those were the numbers that we put for our range. So it's very easy to figure out what the domain and range are. Just figure out what x or what y values make sense, and then that's going to tell you the domain or the range. You could try this one yourself. Pause any of these examples and see if you get the idea of how you can identify the domain or range of a particular graph. So here, if we were to follow the same pattern, let's start with a range this time. We have one y value here that makes sense. We have another y value here that makes sense. And why we say that is because were we to move either left or right, we would end up some kind of way on our point indicating the relation. So moving left or right, we're going to get to a point. So we know 3 is included, but we could say the same thing for anything in between these two. So I move left, there's a point. I move right, there's a point. So these values here between 4 and 3 are also included. And if we follow that same reasoning, we're going to see that all of these points between 0 and 4, including 0 and 4, are going to be included. The difference this time is there are infinitely many points, and nobody's going to sit down and write down every single point. You don't have enough time to write down every single point that fits this description. So we want to write down an inequality to express our situation here. So we said that x has to be between 0 and 4 for the range. It's going to include 0, so it can be greater than or equal to 0. The or equal to, that line at the bottom, tells us that it can be that 0 can be included, but we know the same thing about 4. 4 can be included as well. So our range is x is between 0 and 4, or x is less than or equal to 4 and greater than or equal to 0. We can use similar reasoning to figure out what values of x make sense. So obviously -3 has a value that makes sense, -2 has a value that makes sense, and so does everything in between -3 and -2. Were we to follow the same line of reasoning, we'll see very clearly that what we're dealing with is all of the points between -3 and +2 on the x-axis. So our range, our domain is going to be the set of x values, and I just realized that I made a mistake. Down at the bottom, our range is a set of y values, and I know I said it repeatedly, but somehow still managed to write down x. So when you do this in class, please make sure that you check very carefully before you submit your work, because just like how I made a mistake, you can do the same. So check your work very carefully. But in any case, for our domain, we know that it's going to be between -3 and a +2. And since both of those values are included, we're going to put an or equal to on both of those. So keep in mind that since this point was included, we put an or equal to. So there's a full circle here. This point is included as a part of the domain because it has a value here. So we have to put an or equal to as a part of our domain. Same thing here. This point is included, so we have to put an or equal to right next to the 2. If it weren't included, it would have a hole right here and right here. If this point weren't included, it would have a hole right here and right here, and we would not write this line down at the bottom. But we'll see some examples of that later. So in this question, we're asked to find the domain and range. And some people are going to think that for this particular graph, that it stops at -4, since you don't see anything out here, and it stops at 3, since you don't see anything out here. This graph, though, is something called a parabola. And even though we're limited here because we stopped at 7 on the y-axis, if we were to continue, and we'll see some examples in class, this graph would actually continue out indefinitely. And if you follow back down to the y-axis, so I'm just going to draw this out a bit. So technically, our graph continues on out forever in both directions. What that means is that were we to follow it down, it does not stop at 3. Our domain actually continues. So 4 is included, as well as the points in between. 5 is included, as well as the points in between. 6 is included, as well as the points in between. 7 is included, as well as the point, and even past that. So every number on this side of our x-axis would have some matching point on our graph or our relation. So same thing over here. This is actually a symmetric graph, and so whatever happens on the right side of our graph is going to happen on the left as well. So notice +1 is included, so is -1. +2 is included, so is -2. Were you to look at any of these points here, eventually they're going to match up to a particular x value. So what that means is that our domain would be every value on the x-axis. So how do we express that? Well, we could say that our domain would be all real numbers. All real numbers. Or some people like the shorthand notation. This means the same thing. Putting this fancy scripted R to indicate that the domain is all real numbers. So every number that you can think of, whether you can write it as a fraction or not. For the range, we'll notice that there are no, let's say I use -1. If I go left or I go right, I'm not going to meet up with any point on this graph. So -1 is not included. Same thing with -2. If I go left or right, I'm not going to find anything on the graph. So I have to start here at 0. At 0, I have some value that's on the graph. At 1, I have at least one value on the graph. At 2, same thing. So from 0 up, we're going to have values that are related to our relation. So the way that we would express that is that the range would be y greater than 0. Could you identify the domain or range for this particular set of values for this relation? Well, we'll notice that the x values that we have here, for this point, we're at -5. For this point, our x value is at -4. For this point, our x value is at -2, and so on. And you might be saying, how are you getting these numbers? The scale that we're using is 1. So this is our origin. So if we're counting left, it's going to be -1, -2, -3, -4, -5, -6, -7, -8. It's actually indicated here what our scale is. So our domain here would be the set containing -5, -4, -2, +1, +4, and +5. The range, similarly, would be the y values that correspond. So this point has a -1 for its y value. This point has a +1 for its y value. This point has 0 for its y value, and we can keep going. But were we to describe that, this set of discrete, unconnected points, the set of non-continuous points, would be the set containing 1, -1, 4, 2, 0, and -4. And we could put those numbers in order if we'd like to, but at this stage it's not really necessary. See if you can use the same kind of reasoning to identify the domain and range of this particular relation. We're using the same scale here. So we notice that 0, x equals 0 has a value, x equals -2 has a value, x equals 4 has a value, sorry, x equals -4 has a value, x equals -5 has a value, and so on. So this is what our, factoring in the other points, this is what our domain would look like. Similarly, for our range, we're going to need to identify the appropriate y values. So this particular point has a y value of -4. This particular point has a y value of -2. This point has a y value of -1, and we can keep going in the same way. And this one has a y value of 0. I apologize. This one has a y value of -4. So were we to continue, this is what our range would look like. So here's another relation that we can analyze. So here's our relation here in black. The domain would be the set of x values that somehow have a relationship with a point. You'll notice that our relation has this fully filled in point here. And so we're going to have a fully filled in point here that for the x value that matches that. Similarly, there's a deleted point here. So there's a deleted point here. Notice when we do the range, it's going to be the same thing. Our fully filled in point here has a y value that is fully filled in as well. Our deleted point has a y value that is deleted as well. What that means is that this is a boundary point that is not included as a part of our domain. But this is a boundary point that is included as a part of our domain. And how we express that is, as we said before, with an or equal to, or a strictly less than or greater than. So here as an example, this point is -1, -2, -3, -4. So x is -4 right here. So -4 is included. Notice that we put an or equal to right next to the -4. So that's that line down at the bottom. That indicates that it is a part of our relation. So similarly, this is a +3. So 1, 2, 3. The x value here is a boundary point that is not included. So it's a boundary point, but we don't put the or equal to because this is a deleted point. Same thing with the range. So this 5, y equals 5 here, was not included, so we don't put an or equal to sign down here. This -2 was included, and so we do put an or equal sign down there. Try to see if you can find the domain and range of this relation. Well, we'll notice first that for the domain that there is a deleted point here. This deleted point corresponds to an x value of -1, -2, -3, -4. So we know -4 is a boundary point and it is not included, so we don't put an or equal to. Similarly, for our other boundary point, that the final point on our end here, this corresponds to where x is 2. And here we have a fully shaded in point, so it is going to be included. So we put our or equal to. So that's how we would get our domain. Our range would be done in a similar manner. So notice that up at the top here, this point corresponds to where x is +1, 2, 3, 4. So +4 is an upper value. But let's just notice that the point that it corresponds to is it is not a shaded in point. It is a deleted point. So this value is a boundary point, but is not included. So here, +1, 2, 3, 4 is a boundary point that is not included. We're not going to put an or equal to. It's just going to be a strict inequality. So we're going to have as an upper bound positive 4. Also, for our lower value, our lower bound here, that this value here, which corresponds to negative 1, that it is included since we have a fully shaded in point here. So this negative 1 is included. Do you remember how we would express it? We would have to put an or equal to. So this is our domain and range for the graph shown here. Pause it at any time and see if you could determine why this is the domain and range for this relation that is shown here. Notice that the smallest value that we can have for the range is here. That the smallest value that is going to be any kind of y value is going to be a negative 4. We're going from this point up, we're going to have some kind of way a connection to the graph. So we're going to reach one of the points on this black graph here if we were to use any of the points above. So anything above negative 4 is okay. Even though when we are at this particular point, when we go left, we're not going to touch anything, but when we go right, we are. The fact that it's going to continue here, and that's what the arrow right here indicates, the fact that it's going to continue upward indicates that we have other y values that we can use. So any point up here, if we go right, we're going to reach the graph some kind of way. So y has to be greater than or equal to negative 4 because this point obviously is included as a part of the graph. It is not a deleted point here. For the domain, same thing. We want to see, first of all, the smallest value that we can have if there is one. So on the negative side, we'll notice that the smallest it could be is here. And there's a connection at every other x value as we go right. So the smallest that it could be, the least that it could be, is negative 2. So x has to be greater than or equal to negative 2, again because this point is included. If this were a deleted point, this would be a deleted point, meaning that we would not put this line here. But as this point is included on the graph, then this is included as well as a boundary point. So that boundary point is a part of our domain. Try to see if you can come up with the domain and range for the given graph. In terms of the range, we notice that there's an upper bound here. We cannot go past this point. If we go, let's say, to this y value and go left or right, that we're not going to run into any part of the graph. So the highest value that it can be appears to be a positive 4. And we do have some connection as we go below positive 4. So the way that we're going to express the range is that our y values are going to be less than or equal to 4. And remember, y is equal to 4 did have a point here, so it was not deleted, so it's included. We have to put the or equal to down at the bottom. For the domain, we're going to do something similar. For the domain, we want to see if there's a least or greatest value that we can have. And as we can see clearly, as we go along the x-axis, there's nothing over here that has any kind of connection to our graph. So it looks like the greatest that we can have here is -1. Anything less than -1 will also have a connection to the graph. Notice there's an arrow here indicating that even if we were over here at -8, that eventually, if we were to continue the graph, eventually we would end up with some connection. So the way that we're going to express this is by writing the following. Our x values have to be less than or equal to a -1. So that would be our domain. Try to see if you could figure out why the domain and range for this relation is demonstrated on that graph, or at the bottom, I should say. So notice that the smallest value we can have as an appropriate x value is -8, and the largest we can have is +8, and we have some kind of connection to the graph in between that. So, I'm sorry, I said -8, but I meant to say this is a -7. -8 is actually here. So the smallest we can have is -7, and the largest we can have is 5. And so our x values are going to be between -7 and 5, and it's going to include these boundary points. Because again, notice that this point and this point were included. So that's why our domain is what we see down here. For the range, same thing. The largest value that we can have is going to be here, and the smallest value we can have is going to be here. So our y values are between -3 and +3, and again, these are connected to some point on the graph, so they're going to be included. Try to see if you can come up with the domain and range for the relation that is described here. So the smallest x value that we can have is going to be here. So that corresponds to -1, -2, -3, -4, -5. So -5 is the smallest value we can have. And the largest value we can have is a +3. And those values are included because we can see clearly that those are not deleted points. So we would describe the domain the following way. It's the set of x values that are less than or equal to 3, but also greater than or equal to -5. For the range, we'll notice that the smallest it could be is -3, and the largest it could be is a +3. So our y values for the range are going to be between and including -3 and +3. A function is a type of relation. As we've been discussing relations, we want to see a bit clearly about what this means. And essentially what a function is it assigns one element in the domain to only one element in the range. So how we can understand this word with something that we already know is, let's say that we bought a movie, and let's say it's Transformers. So we put this into we input Transformers, and on the TV we end up with Transformers. So everything functions or works. So that's a good thing. But what if we got the same movie, and we know there's only supposed to be one movie on there, and sometimes when we input the disc we do get back Transformers, But sometimes we input that same movie and some kind of way, we don't know how it happens, but Spider-Man shows up on the screen. So we know something is wrong. This is a situation where something is not functioning. So a function is just a way of saying that is working the way that it should. That if we input one value, so if we have one value in the domain, we expect it to match one value in the range. If we input something and end up with two different values, then that is not a function. One way to determine if it's a function or not is using something called the vertical line test. And all this is saying is that if we have one x value, we don't want to have two different y values. So as an example, this point, this x value, if we were to go up or down, we'll notice that there is no other y value that's associated with this x value. There's only one point here. Same thing here. We go up or down and there's only one point, one y value that's associated with that x value. And we can do the same thing with any of these. There's only one point associated with any of them. So clearly the graph that we have here is a function. So let's apply what we know to determine if we have a function or not here. To determine if these graphs are functions, we want to determine if each value in the domain corresponds to only one value in the range. So let's look at our domain values. We know that -4 is in the domain, -3 is in the domain, 0 is in the domain, 3 is in the domain, and 4 is in the domain. And we have to check every single one of these to see if there are two y values that match that particular x value. So if we were to draw a vertical line to determine that, because every point on a vertical line has the same x value but different y values, then that's a sure test we can use to determine if there is a discrepancy or not. So it looks like the first value, -4, passes the test. There's only one point in the relation that's on that graph, on that line. -3 also passes the test because there's only one point that matches our description. So only one element, that -3, only goes to one element in the range. If we check 0, well, let's not check 0 yet. For 3, that seems to do okay. For 4, that does okay. But when we get to 0, you'll notice that when we draw a line, so we do intersect one point here, but if we continue the line, now we have another point here. In other words, 0 would be input, and then we might get back 0, or we might get back 5. So in other words, we input 0, we get back 0, or we can input 0 and get back 5. So this is not a function. It fails the vertical line test, so it's not a function. If we do the same thing on the second graph, so we draw vertical lines, this one's okay, this point's okay, that point is okay, that one, oh, looks like there's a problem here. So this would not, neither of these relations are actually functions. So essentially a mapping is another way to describe a relation. So we've seen where we've described relations with points on the coordinate plane or ordered pairs, but a mapping is another way. And here's what a mapping would look like. So we know that the domain of this set would include 2, 3, -1, and 0. So the domain would be 2, 3, -1, and 0. And it says to put them in order. We don't have to, but let's just go ahead and do that in this case. So if we're going with what's the least, then -1 would be the least here. So -1 is the least. Then 0 would be the next smallest. And 2 would be the next smallest. And 3 would be what we have left. With the range, the smallest value in the range is 4. And notice that 4 shows up twice in this list. We don't need to write it more than once. 5 would be next. And 6 would be the final value. So let's go ahead and write how these are related. So if we focus on the first ordered pair, looks like 2 goes to 4. So 2 goes to 4. So if we input 2, we get back 4. For our second ordered pair, if we input 3, we get back 5. For our third ordered pair, if we input -1, we get back 4. And finally, for our fourth ordered pair, if we input 0, we get back 6. So if we were to check if this is a function or not, remember we're trying to see if we input something and end up with 2 different answers for that same input, or 2 different values for that same input. So if we input -1, it only goes to 4. 0 only goes to 6. 2 only goes to 4. And yes, I know that we have 2 numbers here going to the same number, but that's okay for it to be a function. We just need to make sure that 2 doesn't go to 4 and something else. That -1 doesn't go to 4 and something else. 3 only goes to one number as well. So this is a function. Use the same reasoning to determine if what we have here in either of these mappings would be a function or not. So in the first one, our domain would include the following values. And our range would include the following values. Based on the ordered pairs, the mapping would be the following way. Notice that -1 only goes to one number, 0 only goes to one number, 3 only goes to one number, and 4 only goes to one number. So this is a function. For our second mapping, the domain would be the following. Notice that 3 appears twice in the domain. We don't need to write this twice. Let's just write it once. The range would be the following set of numbers. And our mapping would be the following way, based on our ordered pairs. Notice that 3 gets assigned to 3 and to 4. So in this case, that's like putting the movie in and ending up with Transformers one time and ending up with Spider-Man the other time. So this does not function. This mapping is not a function. Let's do some more practice. Can you determine the domain and the range of the following relation? So remember that a relation may be listed not just as a mapping or an ordered pair or a graph, but it might also be stated as a table, as we have here. What we're looking for is if the x value gets assigned to more than one y value. And we see here 6 only goes to -2, 9 only goes to -1, 0 only goes to -2. But there's a problem here because it looks like 1 is assigned to 3, but 1 is also assigned to -3. So we have the same x value, the same input, going to two different outputs. So that does not function. It's like saying the same movie is giving you two different movies on your screen. So something's wrong there. This is not a function. Regarding what the domain is, though, the domain would be the set of values that are our inputs. The domain here is the set containing 1, and we know 1 shows up twice, but let's just write it once. 1, 6, 9, and 0. Our range would be the set of y values or outputs that we end up with. So in this case, we end up with -3, -2, -1, +3, and -2. Based on what we just discussed, does this table represent a relation that is a function? Well, 18 only goes to 4 and 2500ths. 20 only goes to 4 and 4000ths. 21 only goes to 5 and 2500ths. 14 only goes to 5. And yes, I know it's 5.00, but just like money, 5.00 is $5. So you can write it as 5.00 or just 5. But in any case, each input gets only one output. So yes, this is a function. The range would be the set of outputs. So in this case, 4 and 2500ths, 4.40, 4 and 4000ths, 5 and 2500ths, and 5. That would be our range. Our domain would be the inputs. So 18, 20, 21, and 14 would be our domain. So a rule is just a set of instructions that tell you exactly what you need to do. And for a function, we might have a rule that tells us how we're handling our inputs, what we're doing to our inputs to get our outputs. In this case, we can see very clearly that all we're doing to our inputs is just adding 4. So in other words, to get our outputs, what's equivalent to that is taking our inputs and adding 4. This may also be expressed not just with y, but what's called function notation. So instead of y, they might use f of x. It means exactly the same thing. So that instead of saying y equals x plus 4, they'll say f of x equals x plus 4. We'll find out later on why it is that there is a difference in the notation. Why have two different ways to write the same thing? But for right now, just understand that this and this mean the same thing. Notice we have the 4, the plus, the x, the equal, and all we're saying is that y is the same as writing f of x. See if you can come up with an appropriate function rule using y equals and f of x equals to express this function. Alright, so in order to do that, a good thing to start with is to figure out, and we're going to find a much easier way to do this later on, but we want to figure out what's going on here. A good place to start is to think about using the pattern, what's happening at 0. So at 0, you're getting 3. We know if we multiply any number by 0 or divide 0 by any number, we end up with 0. So obviously we're either adding or subtracting to get 3. So we know we're going to have to add 3 to 0 to get 3. There may be something else that we're doing, but let's see. If we added 3 to 2, we're not going to get 4. So it appears that there's something else that we're doing as well. So what I like to do is just roll it back. What if we know we're adding 3 to get the numbers here, what if we subtract everything by 3 just to see what's going on? So 6 take away 3 is 3. 4 take away 3 is 1. 3 take away 3 is 0. And 1 take away 3 is negative 2. So how are these numbers related? We'll notice that 3 is half of 6. 1 is half of 2. Negative 2 is half of negative 4. And if we take half of 0, it's half of nothing is still nothing. So it appears that we're also taking 1/2 of each number. So let's say that we wrote that down. We're taking the x values, and then we're either going to write it as, let me write that somewhere else. We're taking the x values and we're either saying we're multiplying it by 1/2 or we're dividing it by 2. Both of those mean the same thing. We said that we're also adding 3. And when we do that, we're going to end up with our y values. So it appears that y equals 1/2 x plus 3, or y equals x over 2 plus 3, which both of those mean the same thing, is going to be what we're going to need to do in order to apply our function rule. Written in function notation, it would look like f of x equals 1/2 x plus 3, or f of x equals x over 2 plus 3. Both of those mean the same thing. Let's just do a quick check to make sure everything here is okay. If we put 6 here, 6 times 1/2 is 3, and 3 plus 3 is 6, which is what we have here. If we put 2 times 1/2 is 1, and 1 plus 3 is 4. So it seems like it's working. I'll leave the rest up to you to check, but notice that if we put the same thing here, just to emphasize that it's the same thing, if we input 6, 6 divided by 2 is 3, and 3 plus 3 is 6. And we would end up with the same result with all of these if we were to use that equation or that function rule as well. See if you can write a function rule that expresses this information. Alright, so this here says the exhibit of a desktop computer. We don't know how much that is, but let's just say that we use y to express that. Is the same as saying is the same value or is equal to. And then it says 20 times the size of a normal desktop computer. We don't know how much a normal desktop computer is, but we know we'll have to multiply it by 20. So what we end up with is y equals 20x as our function rule, where x represents the normal size desktop and y represents the exhibit of a desktop. In this information, we want to determine what the independent or dependent variable is. So what is it that we would need to know first? That would be the independent variable, and the result would be the dependent variable. In this case, we would need to know how many ounces of salad in order to figure out its weight, because it says that it depends on its weight. So we need to know how many ounces first. So the weight of the salad is going to determine the price of the salad. So the weight would be the independent variable, and since the price depends on that, the price would be the dependent variable. Normally the dependent variable would be y. So we're going to say that the price, we're going to express that with y, and we're going to express the weight with x. So here we have something that says the salad cost. In other words, the price of the salad is going to be equivalent to something. And it says 19 cents per ounce. So that means that we're putting it all together. We're going to have to multiply 19 cents times the weight, or the number of ounces. So that's our function rule. To figure out how much an 8-ounce salad would cost, remember 8 ounces would be the weight. So we would use this function rule and input 8 for the x. So y equals 0.19 times 8. I know I could do this as a calculation somewhere else and just give you the answer, but let's look at how this would work out if we had to multiply it. So this would be done on a separate sheet of scratch paper. Notice I wrote it off to the side so that it doesn't confuse my calculation. 8 times 9 is 72. Put my 2, carry my 7. 8 times 1 is 8, plus 7 is 15. Put my 5, carry my 1. 8 times 0 is 0, and 0 plus 1 is 1. I know that there are, in this whole multiplication problem, 2 numbers behind the decimal, so we'll put our decimal there. So it would cost $1.52 for 8 ounces of salad. Remember that a function rule is basically an equation. And just quickly, we want to remember that y and f of x mean the same thing. So if we have y equals 2x plus 3, it can also be written as f of x equals 2x plus 3. They mean exactly the same thing. Also, when we find a value of x, when we're inputting, and we get back a value of y, these go together, so we can write it as an ordered pair. So we can use a table to figure out what ordered pairs make sense in our function rule. So let's apply that and see if we can determine what are some values that would make sense for this function. And we're going to do that for the purpose of graphing the functions. Once we get those values, we plot the ordered pairs, and depending on the situation, which we're going to discuss it in class, we're going to sometimes connect those values. So here, let's pick some, we always want to pick some negative values, some positive values, and 0 to make sure that we have a graph that makes sense. So let's say that we pick the following numbers. Normally we are not going to have the process column. That would be something that we would do on a separate sheet of paper, but let's see what would happen if we were to input those x values. So if we input them, we would end up with, let's see, 2 times negative 3 is negative 6, and negative 6 plus 3 is negative 3. 2 times negative 2 is negative 4. Negative 4 plus 3 is negative 1. 2 times 0 is 0, and 0 plus 3 is 3. 2 times 1 is 2, plus 3 is 5. So to graph this function rule, we would need to plot the points negative 3, negative 3, also negative 2, negative 1, 0, 3, and 1, 5. We're going to see a bit more about how we can exactly do that with the following examples. So suppose that we had this example here. You may try it yourself first, graph it, and see if you come up with a graph that looks like the one that I have. Later on, we're going to learn much simpler ways to graph, but this is the most basic way to graph any what's called linear function. So these are going to be linear functions. When we graph them, these examples are going to turn out to be lines. So if we chose the values 4, 2, 0, and negative 4, since we have to know our x first, x is going to be the independent variable, and since we're going to get back y, or f of x, that's going to be our dependent variable. The value of y depends on what values of x we choose. That's why y is the dependent variable. If we input those values, so 4, 2, 0, and -4, so 3/4 of 4 is 1, 1 take away 1 is 0, 3/4 times 2 is 6/4, and 6/4 take away 1 is 1/2. If we were to put in the y values that we got, this is what it would look like. All we would need to do is to graph the ordered pairs. So the first ordered pair would be 4, 2. The second ordered pair is 2, 1/2. The third ordered pair is 0, -1. And the fourth ordered pair is -4, -4. So let's start with 4, 2. With 4, 2, we would know that our x value is 4, our y value is 2. So we start at the origin, and along the x-axis, we're going to look for 4. Then we're going to find a positive 2 on the y-axis. So our point is going to be here. So we've graphed that point. Now let's do 2 and positive 1/2. So x is 2 and y is positive 1/2. So we go along the x-axis and find 2, and then on the y-axis we find positive 1/2. Notice though, on the y-axis we don't appear to have 1/2, but we know 1/2 is in the middle of 0 and 1. So we would end up here for our graphed point. So we're done with the second point. For this one here, x is 0, y is -1, so x is 0 here. We're not going left or right, and y is -1 is here, so we're going to put our point there. So we've graphed that point. Now we have this point -4, -4, which both of these are negative, which means we're going to be in the third quadrant. So somewhere in here. So x is -4 right here, and y is -4 right here. So that's where our coordinate would go. And since this is what's called a continuous function, we're going to discuss that later on, but you're going to discuss it more when you do calculus and pre-calculus. But since this linear function is continuous, we're going to connect the points and end up with this graph. So that's how we would graph the function y equals 3/4 x minus 1. But of course, we're going to learn a much simpler way to do this later on. Try to see if you could use the same principles we've just discussed to graph this function. So we need to choose some values, and I've chosen some here. Were we to input them, we have 5 here, 0 here, -1 here, and -5. When we evaluate those functions, those equations, this is what we would end up with. So now we just need to graph these. I'm not going to write them as ordered pairs. Hopefully we see from the previous example how to do that. But we should know that this is our first ordered pair. This is our second ordered pair. That's our third, and that's our fourth. So for 5, -8, x is +5 and y is -8 would be down here somewhere. We don't have enough room to graph that. It would actually go beyond the space that we have here. So we'll just graph the next point. 0, 2 would go here. Negative 1, 4 would go here. Negative 5, 12. Okay, looks like we don't have enough room for that one either. But we know that if we did, connecting the points that we have, we end up with this line. So that is our graph, y equals negative 2x plus 2, or f of x equals negative 2x plus 2. Let's take a quick look at arithmetic sequences. So arithmetic sequence, a sequence basically is a list of numbers. So it is what it is. We're going to see exactly how we can apply this formula that you see here to come up with a sequence or to come up with a particular term in a sequence. Remember that this D stands for the common difference. So just a quick example here, if you had 3, 7, 11, 15, and so on, if you had this sequence, notice that the difference between 3 and 7 is 4. 7 and 11 is 4. 11 and 15 is 4. So the common difference here would be 4. A is the first term in the sequence. So what would go here is 3. So we're going to use that to determine particular values of a sequence. So suppose that we had this situation here where we had to find the second, fifth, and ninth terms of the sequence that's described here, where the first term is 2 and the common difference is 3. When n is equal to 2, what we're talking about is the second number in our sequence. So we have, for our second position, and we could write a sub 2 if we like to, or a with parentheses and n, but it's better stated this way. For the second term, n is equal to 2, and what we mean by that is, in a sequence we have the first number, the second number, third number, the fourth number, and so on. So here, the first place we always say n is equal to 1. In the second place, n is equal to 2. In the third place, n is equal to 3, and so on. So we're just applying that in the formula. So since we have to find the second number, we have to take the first number in the sequence, which appears to be 2, and add it with this expression here, noting that the common difference is 3. If we evaluate it, 2 minus 1 is 1, 1 times 3 is 3, and 3 plus 2 is 5. For the fifth number, a sub 5 is going to be equal to this expression here. 5 minus 1 is 4, 4 times 3 is 12, and 12 plus 2 is 14. Finally, for the ninth term, n is equal to 9. So 9 minus 1 is 8. 8 times 3 is 24, and 24 plus 2 is 26. So the second term would be 5, the fifth term would be 14, and the ninth term would be 26. So let's apply what we know to find the next two numbers in the following sequence. So we want to find the fifth and the sixth number in this sequence. To find the fifth number in the sequence, we'll know that the first number here is negative 5, and so we put negative 5 in place of the a. The common difference, as clearly seen from here, is going to be 3. Were we to subtract the rest of these, we will see that 3 is our common difference. A positive 3 is our common difference, and so that's what we're multiplying by here. 5 minus 1 is 4. 4 times 3 is 12. And 12 plus negative 5 is 7. So the fifth term in our sequence would be 7. To figure out our sixth term, we're doing exactly the same thing, but instead of a 6, we're going to put a 5. 6 minus 1 is 5. 5 times 3 is 15. 15 plus negative 5 is going to be 10. So the sixth term is going to be 10. Notice that the common difference remains the same. Between the fifth term and the sixth term, if you subtract them, you still end up with 3. Pause it and see if you can work this one out yourself. To figure out the fifth term, we're just going to put 5 for our n, and notice that the common difference here is negative 4, since these numbers are decreasing by 4 each time. 5 minus 1 is 4. 4 times negative 4 is negative 16, and negative 16 plus negative 6 is negative 22. For our sixth term, we're going to do the same thing, but instead of 5, we're going to put a 6. 6 minus 1 is 5. 5 times negative 4 is negative 20. Negative 20 plus negative 6 is going to be negative 26. So the sixth term is negative 26. In this section, we'll look at a direct variation or direct variations and see exactly what those are and how we can apply what we know to answer particular problems. A direct variation basically means that we have a constant ratio between the x and the y values. So if we put y over x, we're always going to end up with the same number. So y divided by x will always be a constant. Or if we could say we can take each of the x values and multiply by a certain number to get the y values, and this is consistent, then we're dealing with a direct variation. In this situation, we know that we have a direct variation because if we put the y and the x in a ratio, let's say we took the first set of values, 12 over 6 is going to be 2 over 1, or just 2. Similarly, 14 over 7 is going to be 2 over 1 if we reduced it, or just 2. Also, lastly, 16 divided by 8 is also going to be 2, and since all of these are equal, so 14 over 7 gives us the same value as 12 over 16 over 6, which gives us the same value as 16 over 8. They're all equal. We're dealing with a direct variation. Besides that, we also want to know what our constant is. So notice that what remains the same for all the ratios, what remained constant was a 2. So our constant of variation is 2. We can also say that what we're doing to each of these x values here is multiplying each of them by 2 by that constant to get y. So 2 times x would give us y, or y equals 2x. So we can think about it as our constant is 2. We can express our direct variation either as y equals 2x or 2 equals y over x. Here's another example of a direct variation. Notice that if we were to write a ratio for each of these numbers, y over x, that we would end up with 10 over 30 being reduced to 1/3, that 5 over 15 would also reduce to 1/3, that 3 over 9 would also reduce to 1/3. So it looks like our constant of variation is 1/3. 1/3 remains the same. So if we were to write our equation, we could either write it as y over x equals 1/3, or we could write it as y equals 1/3 x. So either of these would express our direct variation as described in the table. Here's another example. Pause it and see if you can come up with the constant of variation and the equations, how we can express the equations that this direct variation is an expression of. If we did the ratio -1 over -4, or -1 divided by -4, a negative divided by a negative is a positive, so this is really a positive 1/4. Similarly, -4 over or divided by -16 would end up being, if we divide by -4 over -4, end up being 1/4 when we simplify it. -10 over -40, a negative divided by a negative is a positive, and so it also becomes 1/4. Therefore, our constant of variation is 1/4. So we can write it as y, our equation as y over x equals 1/4, or we can write it as y equals 1/4 x. Look at what we have here. Based on what we discussed, are both of these going to be direct variation? And if not, which one is and which one isn't? Remember that a direct variation can either look like the ratio y over x equals k, or it can look like y equals some number times x. Notice that in this example where it's written as y equals, we're not adding or subtracting. So it's going to be different from this. This is not a direct variation. However, remember that it's y equals some constant times x for a direct variation. In this case, the constant is 5. And so this is a direct variation. Solve for y and determine if either of these are a direct variation, y or y not. Alright, let's start with the one on the right. If we were to add 6y to both sides of our equation, we'll notice that these two would eliminate, and that would leave us with 5x equals 6y. If we were to divide both sides of our equation by 6 in order to isolate the y, we would end up with 5x over 6, or 5/6x equals, these divide out, equals y. So in other words, we end up with y equals some constant using the symmetric property. Y equals some constant times x. So this is a direct variation. On the other side, to isolate the y, we can divide both sides of our equation by 2. These eliminate, and we end up with y equals either 2.5 or 5/2 x plus 1/2. And since we're adding something here, this is not a direct variation. And I forgot to say something here about this one here. The constant of variation in this example is going to be 5/6. Let's look at some examples of how direct variations would work out in a word problem. So in this situation, it says that y varies directly with x. So we know that direct variation is what's implied here. And that means that y over x is going to be equal to some constant. And it doesn't matter what x and y are, as long as they're part of the direct variation, that they're going to be equal to a constant. So if we start out with the statement that not just that it varies directly, but y is 28 when x is 7, that's a ratio. So y is 28 when x is 7, and that's going to be equal to some constant. But we also know that they describe the other y value as 52. So our other y value is 52, and we're trying to find out what x is. So we would need to solve this proportion in order to determine the value of x. Notice that the numerator here is 4 times the denominator, and since they're equal, we expect the same thing to happen here. So if this is 52, we would divide it by 4 and end up with x is equal to 13. If you use the cross product here, it would be a whole lot of unnecessary work, so we have to work smart. We know that y varies directly with x again here, so we're talking about a direct variation. They state that y is 4 when x is 3, so y is 4 when x is 3, and they say that find x when y is 12, so y is 12 and we need to find x. So we would need to solve this proportion. The most effective way to do so in this case is to notice that 4 times 3 is 12. So if we multiply this ratio by 3 over 3, then we would end up with x equals 9. For the bottom problem, we're doing exactly the same thing. It varies directly. Y is 6 when x equals negative 5. So y is 6 when x equals negative 5. And they want us to find out this time what y is when we know that x is negative 8. So the best way in this case to solve for y is, the only thing that you would probably make sense here is for us to do a cross product. So we know that with a proportion, the cross products are equal. So if we multiply diagonally, 6 times negative 8 has to equal negative 5 times y. 6 times negative 8 is a negative 48. So negative 48, it has to equal this product, negative 5 times y, which we're going to write as negative 5y. To solve this, we would divide both sides of our equation by negative 5 to isolate the y, and we would end up with y equals, a negative divided by negative is a positive, so we have a positive answer. It's going to be 48 over 5. And we could stop here, but if you want to go the extra step, it would be 9 and 3/5, or 9.6. Here's another situation. Try and see if you can solve this one on your own before we work it out. So it says here that there is a varying directly, so this is a direct variation problem. And it says that the distance traveled varies directly with the amount of gas used. So which one of these is the independent and which one is the dependent variable? Well, the distance that it travels is going to depend on the amount of gas that's used. So we're going to do y over x. That's going to be distance over gas. It says that a car uses 8 gallons of gas, so 8 gallons and travels 290 miles. And they ask us how much gas, so we don't know how much gas is going to travel on 400 miles. So we have to figure out how to answer this question. We could simplify the ratio on the left to be 145 over 4, and that's still equal to 400 over x. And we can use the cross product. So 145 times x is going to equal 4 times 400, which is 1,600. If we divide both sides of our equation by 145, then we end up with x equals 11 and 5 over 145, which we can reduce to 11 and 1 over 29. So here's another situation. Try and see if you can work this one out yourself first, and the answer is going to appear shortly. So try and pause it, work it out yourself, and then see if what you got is what I got. So again, notice that it's going to vary directly here in the problem, so we're dealing with the direct variation, and so it's going to be y compared with x. His wages, y, are going to depend on the number of hours that he works. So if we were to express this, so y would be wages and x is hours. We're going to put those in a ratio. His wages for 5 hours, so his wages are $29.75 if he works 5 hours. And they're asking how much will they be, so how much will he work how much will he earn if he worked 30 hours? So this is a particularly simple proportion to solve, because we notice that 5 times 6 is 30. So we can just multiply this by 6 over 6, and we would end up with x equals 178.5. So he would work 30 hours and make $178.50. So let's look at graphically what happens with a direct variation. Because we end up with a graph of y equals kx, as an example, y equals 3x, or y equals 5x, or y equals 7x, or any of those, y equals 2x, all of these have something in common. If we input 0 here for the x, what are we going to get back for the y? Well, 3 times 0 is 0. 5 times 0 is 0. 7 times 0 is 0. 2 times 0 is 0. So in other words, all of these are going to have 0, 0 as a coordinate. So in other words, the graph has to go through the origin if it's a direct variation. So looking at this graph, does it go through the origin? No. So it is not a direct variation. Looking at this graph, does it go through the origin? It comes pretty close, but no, it doesn't. This is not a direct variation. So let's just write this down. Not a direct variation. So same thing here. Not a direct variation. This one as well doesn't even come close. It's not a direct variation, doesn't go through the origin. This one does go through the origin, but any graph that looks like this is going to be a line. You can test out all of these if you like to. So for that reason, even though it goes to the origin, this is not a line. So this is not a direct variation either. So neither of these, none of these are direct variations. We may also have to deal with inverse variations. And all inverse variations mean is that if we multiply the x and the y for our relation, we always end up with a constant. Notice that last time it wasn't multiplication, it was division. So the difference between a direct variation and an inverse variation, this is a direct variation. So when we divide these, we end up with a constant. So direct variation. An inverse variation means that we're using an inverse operation. Instead of division, it's going to be multiplication to accomplish the same result. So x times y instead of y divided by x. So let's test this out if this is an inverse variation. Basically, if we multiply the x and the y, we should end up with the same value for each ordered pair. So 4 times 15, so 4 times 15 is 60. 6 times 10 is 60. 10 times 6 is 60. So in other words, if we take our x values and we multiply by our y values, we end up with the same number, which is 60. So this is the equation of our inverse variation. So this is an inverse variation because each pair of x and y, when we multiply them, we end up with a constant. Let's test if this is an inverse variation or not. If we multiply 2 times 1, we get 2. If we multiply 5 times 2.5, and let's just put that in parentheses since we don't want to have too many dots around, then this would be 12.5. If we did 8 times 4, we would get 32. So obviously we don't end up with the same number. This is not an inverse variation. So not an inverse variation. In fact, I believe that this is actually a direct variation. So let's try division instead. If we did y over x, let's see if we end up with a constant. So if we did 1 over 2, obviously that's equal to 1/2. If we did 2.5 over 5, 2.5 is 1/2 of 5, so yeah, that's equal to 1/2 too. 4 over 8 is equal to 1/2. So it turns out that what we have here is not an inverse variation, but a direct variation with the following equation. Either y equals 1/2 x or y over x equals 1/2. So this is actually a direct variation. So here's some examples to summarize what we've just discussed. Are they inverse variations? Are they direct variations? Let's figure it out. Well, if we were to, let's say we look at the first one here. If P is our y and S is our x, so let's just change the variables. Instead of P, let's use y. Instead of S, yes, let's use x. What does this look like to you? Well, this is a direct variation, which may also be written as y over x equals 3. So this is a direct variation. For the second example, what if we again exchange everything, and instead of t we put y, and instead of r we put x? We'll notice that this is the exact format that we had y equals k over x. It is an inverse variation. And it may also be written as x times y equals 150, or t times r equals 150. And just to demonstrate that, let's say we were to undo this operation to get the 150 by itself. Instead of dividing by r, the inverse would be to multiply by r. And we would do that to the other side as well. So we end up with t times r equals 150. So we multiply the variables and end up with a constant. It is definitely an inverse variation.